with the Higgs mechanism. Let's still stay with one example and continue what we did yesterday. Notice that if I write here, let me just write it here, a general covariant derivative. Or I could just write some charges here. You know, we could imagine many different theories, summing over many different groups. In a sense, understanding the Higgs mechanism is even easier than the Goldstone one, if you wish, generally. Because this will be acting, right, on the, so when it acts on some Higgs field. And we said every time when TA50 is non-zero, we expect symmetry breaking. Here it's easier to see because immediately this guy then will get a mass term, you agree? Unless, of course, there is a linear combination which is not broken, okay, there will be an eigenvalue in the mass matrix. We'll talk about that. But in some sense, so generalization to a multi-group, if you wish, or a non-abelian group, or whatever, it's easier in a Higgs mechanism. If we go through Goldstone, just because it's the sub-case, so it's good to start with that. But even if you don't really learn it, partially for this course, there are things that I want you to understand. But if you understand the Higgs, this is much more important, and it's easier, and it's more direct. But what we have to do, remember what we said yesterday. We have two choices. There was a unitary field that I wrote like this. Let me not rewrite the Lagrangian again, I wrote it so many times. Right? Okay, just to say that I defined d mu to be d mu minus I g q a mu. And I took q5. We have to remember this, to be 1. I normalize. Nothing would change if I keep some arbitrary q there. If it was 2, I could really find the G, you know, one charge I can always take as 1, you agree? So I can as well take Higgs here. That's the only field, but even if there are more fields, 1 I could normalize to 1, the way we did with the electron. We call it 1. It's not that it's really 1. Right, don't keep that in mind that we often speak of fractional charges. There are no fractional charges, that's just a convention. Whole charges are integers. Okay, that's very important. The logical unit would be the smallest charge. This is what you would use as a unit, but historically it didn't happen like that. So in this gauge, what I found out immediately was, it was so simple. I got 1/2 from here, 1/2 G squared, V squared, A mu, 1 plus H over V. Everything was here. The whole beauty, the whole richness of the Higgs mechanism. Gauge boson got the mass, and then learn how Higgs coupled to it. Okay, this was just the covariant derivative square. You agree, because the field is trivial in this case. So we said MA is GV. And the Higgs couples the leading term, the linear term, couples with the G, MA, Higgs A mu. This is mine. Came from this interaction. Extremely simple theory. So transparent, unfortunately you can't work with the theory. Why? It's what Nicolas noticed immediately, there was a problem of the propagate. We repeatedly argued that this is not good. Here I get proper propagator, right? Roca theory. We are fortunate that I can also write the theory due to the original gauge freedom with a different convention, gauge, if you wish, for my scalar field. I could also write it. Notice that there was no different because I was interested in the leading term. I didn't do the whole theory. So the advantage of this, which I call the normalizable, so this was unitary picture, and this was a normalizable. That there was a gauge symmetry, right? Gauge symmetry meant that G goes G plus V alpha. This symmetry remains, but this is a function of x, and A mu goes into A mu plus 1 over G d mu alpha of x. The symmetry remains, therefore I know how to deal with it. I've learned from, I added the gauge fixing term, okay? Here the, more or less the, how did I choose to add this term? Remember what my logic was? Okay, you were saying it looked sort of magical, but there was not really magic. I needed to add an extra piece to the usual gauge fixing in order to eliminate from here. Remember what I got? I got all kinds of interaction, but I had a bad term, which was GMA, G d mu A mu. Remember this from yesterday, okay? I'm just trying to make sure to So obviously I will need to introduce these two terms, okay? So what is the logic? 1 over xi is that if I go to the limit when MA goes to 0, I want to recapture my usual, so obviously in this limit MA goes to 0, I want to recapture. This is why the first piece, when MA goes to 0, I recover the usual gauge fixings that we did in QED. I added an extra term, and it had to have a C piece so that I cancel 1 over C here, so that I cancel this here. And that determined then what happened with. So there was a must. There was no guesswork here. It had to be chosen like this, okay? It was unique to reduce to, so once again, so here when MA is 0, I'm back to the gauge fixing of QED. And I need to cancel. This was bad. I need to cancel bad. That fixed everything. What we found out, and we want to continue today, maybe I write it here. What we found out, I think we'll need them here all the time, so let's keep the propagator for A. K squared, Q squared, I don't know, K squared this time, minus MA squared, G mu nu, plus psi minus 1, K mu, K squared minus CMA squared. I didn't give it as a homework. I could have, maybe. I could have done this. I wonder on the days when I teach at 11 whether there is a hole also in the afternoon. Monday, Wednesday, Friday. Let's be sure, because I, for example, would prefer not to teach. I have this habit of working, okay. I do an experiment. Normally I was teaching at 2 o'clock, okay. Even when I give conference talks, people know that I don't get up early. This is an advantage or a disadvantage of being well known. The people know also your bad habits. I almost never give morning talks, okay. It was like this, I'm pretty sure. Now how do we check it? Let's see how we check it. When MA goes to 0, I reproduce the usual one. When C goes to infinity, I have to get a unitary gauge, okay? So the signs are good. This is just to, okay, with C0, there could be a positive sign, I will still reproduce it. The sign is okay. In the psi going to infinity, I have to get the unitary gauge. When psi goes to infinity, I have not added the guy becomes infinitely heavy, we found out, okay? I should, well, it will be here. Sorry, let's write it here. There is d of g, which is I, k squared minus cma squared. So I want you to remember, I've derived it if you wish. This has a pole at k squared minus ma squared, so the first piece I know it has to look like this. In a sense, it's a derivation. I have to reproduce, it has to go as k nu over k squared plus a linear combination of ma squared. In the limit psi equal, in the limit ma go to 0, I have to reproduce the QED propagator, which I did. It will have psi minus 1. You have to remember this, okay? It will be good that you remember one thing, okay? Then I go look at the limit psi going to infinity, I see that there is no g. Oh, that's a unitary gauge. There was no g in the unitary gauge. So when psi goes to infinity, I get precisely this proca, okay? So in other words, psi going to 0, I get QED, massless guy. Psi going to infinity, I get proca. So I'm okay.
But in the first case, when we take psi to go to 0, we will have two propagators, right? One.
No, not psi going to 0. Ma going to 0. What am I talking about? Not psi going to 0. No, not psi going to 0. No, QED is not psi going to 0. You have to add the gauge fixing term and not with an infinity here, okay?
So what happens if the G at, like, we turn back to QED, but we have a G here?
When? Sorry?
When MA goes to 0.
Yeah.
What happens to 0?
When MA goes to 0, when there is no, I have a massless guy, remember, because when MA goes to 0, remember how I take MA going to 0 here, by V going to 0. So it's V going to 0 when MA goes to 0. Okay, how to say this? Let me do it here. MA going to 0. Well, I started well here. MA is GV. You don't want to take G going to 0. That I said, you know, you can take this limit if you wish, but then there is no photon. It's not a. This is useful just to see what happens when I go to the global case. That's a different story. When G goes to 0, there is no local gauge invariance because there is no covariant derivative. I'm back in the Goldstone picture. But when I say that MA goes to 0, I want to kill the symmetry breaking. I want to go to the photon limit. Photon is coupled. V going to 0, G goes to E, that becomes a photon. Why not? I want to see whether I get the correct theory. So when I say that MA go to 0, I will from now on mean that V going to 0 here. And I'll be specific here. When V goes to 0. Why not I write like this? It's more correct. This is how you should think of the reproducing the photon. And then we said G is massless because in the potential I didn't write, there is no mass term. There is nothing magic here. Imagine I write the Dirac equation without the mass term, okay? That's how we used to write it for, in the old days, for neutrino.
And does it make sense to talk about G? Because I would argue that we said V equals 0 means there is no symmetry breaking, so there is no...
No, there is G, of course.
It just propagates and does not interact. As a
No,
mass.
no, why? It interacts.
But in that limit.
G going to V going to 0, yes. Or G going, which limit? Sorry, again.
In QED limit. In QED limit, can you observe G in any...
This guy?
Yes.
No. But the potential is, remember, the potential is lambda over 4. I'm glad you asked. Look, you see how it's there is so much we can ask, you know. This is why I like to beat that bush, you know. I keep doing one example ad nauseam. Okay, here, making sure that I don't want to just teach it. So when V goes to 0, I mean, I would just have a very complete scalar field, there is G here. Of course, this is a complex field. It's just I chose it to be massless. I didn't write the mass term at all. In the limit v going to 0, I will have, it's not an interesting theory, that particular theory for the scalar field. We don't see such particles. We can imagine them, but we don't like to think of that.
I was thinking like, if you set it 0, it's something like a complex field we have, which has two real.
Right, G is, normally we group together G and H in one particle. When we have the generate two states, we call it one complex particle. Electron, for example. Electron really is a combination of two degenerate states, if you think. Electron field has an electron repositron inside, or EL and ER. They were separate fields. I grouped them together because they are degenerate. It's like, you can think of the electron, we'll come back when we do Majorana. It's like having two Majorana fields which are degenerate, in a sense. Will produce for you a four-component guy, okay? I'm just making you think, running ahead. We will do Majorana very seriously. We have to study fermion mass. It's a deep, profound issue. Independently of just neutrino, you know, as Majorana asks this fundamental question, okay, there may be new particles in nature, and we'll have to have a good understanding of this, but later. So just wanted to show that there is a sort of derivation, quote unquote. If I don't like reasoning, then I go and check it, okay? I invite you to do that, to be at peace with yourself. You know how to invert quadratic form, that's trivial. It's the same as proper. So this is our Higgs mechanism, spontaneous symmetry break. Everything would be here if I had a fermion, but without a fermion, at least one fermion, I have to add one fermion to illustrate what is going on. We want to understand the physics of the standard model, in which, of course, fermions are the main protagonists. We have these messengers, they are important only because they take one fermion into another, right? The messengers without fermions would be nothing. They would be propagating freely in the like the photons that decoupled, right? There are these photons in the microwave background that they are just staying there. And unless you want to calibrate your antenna in a small little place in New Jersey in 1966, I think it was, you would never know them. You know this incredible accidental discovery, the beauty of that. Did you talk already about it to some degree? Or you will start maybe with Paolo soon. He's going to talk about that. That's one of the most mind-boggling accidental discovery. They even got the Nobel Prize, okay? Sometimes. Well, I guess the discovery was important, but they didn't know what the hell was going on, and they couldn't publish the paper for a month. Anyway.
What do we mean by QED there? QED propagator or?
Well, the QED, there will be a theory like QED. The guy will behave like a photon. Now I have to couple it to the fermions, okay? I have to couple it the proper way to the fermions, and then so it's not fair to call it QED before I introduce the
QED
fermions.
for scalar field, or let's say.
Yes, you're right. Okay, this will be a charged scalar field interacting with a particle like photon. Okay, I mean in all the sense it will be okay. You're right. Okay, my word, strictly speaking, I should have used QED. I didn't even introduce the fermion. And I will actually choose the fermion to interact differently with I will discuss it in a second. I'm glad you asked. Okay, QED. QED-like, thank you. This should have been. Okay, master's photon I meant. Sorry. See, it's not easy to be consistent, always. With your language, okay, and I'm glad you asked, okay. I'm actually a language purist, okay. I care a lot about semantics. People think that I exaggerate. I think it's very important, and I'm glad you pointed out. And the point is, will be here. It will not be QED. You will see in the moment why. I need to illustrate. I need to give you an example, and the simplest example of what happens in the standard model. What is crucial in the standard model? That left and right fermions are different, right? Their gauge properties are fundamentally different. So when we introduce now the fermions, so I will have to introduce the fermions. So let me add matter. That means I need to add 2. Now let me use this notation, sorry. Some left-handed and right-handed fermion. Because I'll be using F much more than 3. How do I introduce that? Well, that's very easy. The Lagrangian is simply is the generalized Dirac Lagrangian, right? FL bar, the fermion Lagrangian, d mu FL plus I FL bar gamma mu d mu FR. Now I have to specify the charges. It's all here in the covariant derivative. It's all here in the covariant derivative. All I have to specify the charges for left and right. So it's obviously not QED because I don't want to use the same charges. What is the characteristic of QED? The first and the foremost characteristic is that photon interacts equally with the left-handed and the right-handed. It's a universal interaction that's very important. Parity is not broken. But I want to imitate the standard model where parity is maximally broken. So I will take here, it's up to me to define the theory. This is not QED. So it was obviously a bad choice of word. So in other words, Q acting on FL, we can call that QL. And Q acting on FR, we can call that QR. And I know that what I need to understand the Higgs mechanism that reproduces the standard model, I need QL different from QR. This is the, if you wish, standard model. Again, forgive me the choice of word. A standard model-like picture. The crucial thing about the standard model is that left is different from right. Really, if I wanted to imitate the standard model, maybe I want to tell you that actually I can do it more generally. I could, for example, take QR equal to 0. Right? In the standard model, the left-handed fermions are doublets, and the right-handed fermions are singlets. So the right-handed fermions even don't interact with the SU2. Okay? But I want to show you, as long as QL is different QR, I'm reproducing the picture of the standard model, which means, yes, please?
Q here mean not the ER charge, it's some different charge, right?
Sorry?
Q, which acts in the fermion.
It's this charge Q, whatever this charge is. This is not electromagnetic. I will try to be consistent, and when I talk about electromagnetic, I'll put EM here. Okay. You know that there are different charges. There is hypercharge. Think of hypercharge if you want here, not of charge of the. Now, what is then crucial thing? What would happen if the charges were the same? When the charges are the same, you add to the Dirac Lagrangian, which Dirac implicitly assumed. He wasn't aware that he assumed that. Well, he was aware. He was writing an equation. Sorry. No, Dirac was not completely stupid. I'm sorry. Forget what I said. He wanted to write an equation for a fast-moving electron, right? In which case he had one and the same charge. So he could write his mass term, but he didn't think in terms of the left and right components. He didn't write it like this. He wrote it immediately in the 4 component. This is much better because I can generalize it to the particles, for example, in which left and right is different, like neutrino. There may not even be a right-handed neutrino for as well as we know. Open question. So that means that I cannot write the mass term, you agree? This I cannot write. I took QL different from Q1. And I'm assuming a U1 gauge invariance, therefore there is no mass term. This is the situation we are going to encounter in the standard model. Okay, I'm encountering it here. I'm taking QL different from QR. But I want to describe massive fermions. There are no massless charged fermions. There is even inconsistency. You can't write even the electrodynamic or massless charged fermions. There are problems when the mass goes to zero. Okay, there are mass singularities, but it doesn't matter. There are simply no such particles in this world. Okay, electron has a mass. Down quark has a mass. Up quark has a mass. They're very tiny masses on the scale of the matter as what contributes to you and my mass. Yours and my mass comes all from proton and neutron, okay? But still, this mass is not zero. So what should I do? I have a dilemma here that we are going to face. This is a dilemma that the Weinberg faced in the in Salam. They faced in the standard model. What to do when the fermion is okay? This is why I want to do this UN example very carefully. We see all the physics is here. I can't write the mass term because left is different from right. That's what the world of weak interaction tells me. So I can't write that. What I can write, I can couple it to the scalar field. That is possible, as long as the charges match. This is called the Yukawa interaction, by the way, traditionally. Yukawa had imagined interaction in which the protons and neutrons are interacting with pions. Today we know they are not elementary particles, okay, so it stayed this name. This is, of course, a very different interaction. This is a fundamental scale and nothing to do with a pion, okay. This is our Higgs hidden here. And this is I can do this, you agree. What I run here, let me just say it, and then as long, this is correct, as long the charge of this interaction must add up to zero, Lagrangian is invariant, the charge of this guy is 1, right? So minus QL plus QI plus 1, which I took the charge of phi to be 1 and erased it. Once again. It was this. If I write this, this is okay, you agree?
Yes, I have a question. Why cannot write it in different ways, like FL, F bar, FL, or F, or maybe a combination of them, or like.
How about this?
Okay.
I have to do that.
Yes, but what about also FL bar, FL?
What about that?
It violates something, right?
Yes.
Okay.
Help him. Help your colleague.
Oh, okay. I see.
What does it violate? It violates Lorentz symmetry, right? FL bar FL is not an invariant. Which symmetry does it violate? Remember, left and right fermions are spin and half particles. So if there was no boost, any combination would be invariant under rotation. It's the boost treat left and right differently. Under rotations, left and right are the same particles, okay? They're both spinors. They rotate equally. But left and right, you know, it's sort of, when one moves left, the other guy wants to move right. They have opposite property under boosting. Therefore, you can write FL bar gamma mu FL, but you can't write FL bar FL, obviously. Then you wouldn't write this, okay? Just because there is gamma 0 hidden here. And this is just a normalization of charges. I could have put 5 star here, but I decided to put 5. That's up to me. This is what I call the fields, okay? This is a name. I had the freedom to choose these charges. Okay? This is a complete Lagrangian, and we have to be very careful now. You have to be. I'll try not to look at my notes because I want to do. I hope to do that. A little non-trivial calculation which every sign and factor will matter. We can't make a mistake.
Maybe,
Yes.
Maybe very good question or not, but do we here assume that we transform the mass? That the mass of our particles will be transformed under.
I don't know.
Gauge.
I don't know what's going to happen. There are no massive particles here yet. There is no mass yet. This is just the Yukawa direction. I didn't write the master. Nicholas.
We are discussing U1, so we don't care about the representation of the scalar field, but in general, for a general group, the representation of the scalar field will matter in terms of
In which
writing
sense?
down the invariant.
Well, here also. I'm confused. What do you mean? U1 is the same as in SU2, the same thing. We have to match the charges. In SU2, for example, what will happen in SU2? Let's try to guess. Imagine, in the standard model, okay, let's try to guess. Okay? If it's too early, don't worry. Just relax. Think of what you're going to do in the afternoon. Let's imagine that the left is a doublet and that this guy is a singlet in SU2. What would this guy have to be? It would have to be doublet. So the dilemma that Weinberg had, I can bet your mouse, I can tell you immediately. He had to choose the Higgs. Well, you always know how to choose the Higgs because you need to have a Yukawa interaction. Why do you need to have a Yukawa interaction? Because there is a vacuum expectation value hidden here and this will give it a particular mass. Higgs gives everybody a mass. Why? Because in the vacuum it carries a non-trivial value and therefore whatever interaction you get in that limit will turn into a mass. It gave gauge boson a mass, it gave itself a mass. Now it's going to give a Fermion a mass because phi is where is phi. All I need is this. I'm keeping a linear term, remember? Let me work with the simplest realization of the normalizable gauge. It's up to me. How I choose my variable, it's up to me. So this is, let me write this Yukawa interaction. By the way, I took Yukawa out. I took it to be real. Why did I do that? The gauge coupling has to be real. Gauge fields are real. The gauge coupling has to be real. That's immediately the hermiticity of the Lagrangian. This could have been complex. Why did I choose it to be real? Because I can always make it real. I'll change the phase of FR, for example. The phase of the fermion field is not physical. Even phi is complex, so I could have chosen the phase. But here I choose FR, for example, and I rotate Y. So Y is real. Why is Y real? Because I have a phase freedom. Well, Alexei taught you this. You can keep doing it up till some point. For example, you can do it with one generation, you can do it with two generations, but you can't do it with three generations, remember? There it sort of failed. And Kobayashi Maskawa got a Nobel Prize for realizing that. It was a profound thing, because when there is a phase, there may be CP violation. It requires complexity. But not with one generation, okay? I can always make Yukawa real. So what do I get here? I will get Yukawa. This has phi, look please, there is a real, a complex piece. There will be V plus H. It will have FL bar FR plus FR bar FL. What is that? That's what we call F bar F. You agree? After all, what is a Dirac mass term? That's left, right, plus right, left.
But the terms that we mentioned, FL bar FL and FR bar FR, since they should be zero, we don't say it.
Yeah, I didn't write them. That's what I wrote. All I wrote is, oh, this should be in yours. This I shouldn't have to do here. This is obvious. 1 plus gamma, 1 minus gamma, 1 minus gamma phi, 1 plus gamma phi, add to 1. Right? This is 1 plus gamma phi, this is 1 minus gamma phi, with the 2. They add to 1. This is F bar F. This is why Dirac wrote it like this. He didn't even have to think of left and right. He just put them together. Remember, in our notation, F is actually FLFR. My gamma 0 is the diagonal. Is that? It's not as if it's not completely. Is this in your fingers or not? You better be. Right? This is trivial. Left, right is 1 plus minus gamma 5 over 2. This will have 1 minus gamma 5, this will have 1 plus gamma 5.
We choose here the Broca the unitary representation for U for phi. I mean, because we have the normalizable one and the unitary one, but you write it. You wrote the.
But it doesn't matter which one. These obligate in both representation. The G piece, whether I keep it or not, obligate a thing. Okay. Let's just stare at this piece. You agree? Let me just forget about G at the moment. I go in unitary gauge. This shows the following thing here first: that the fermion got a mass. V times Y is a mass. Y times V, it's obviously fermion mass. And it's always, the Higgs mechanism is here. A particle mass is always going to be proportional to the vacuum exclusion value, that's the only scale in the theory, and to the coupling, which is appropriate to the Higgs particle. In the case of a fermion, it's called the Yukawa coupling. In the case of gauge field, it's called the gauge coupling. In terms of the scalar guy, it's called the self-coupling, the lambda coupling, or the scalar coupling, or 5 to the 4th coupling, and so on and so forth. But every time there will be an appropriate coupling, and the particle will get a mass, okay? Everybody in the standard model, all the particles that we know, when I speak of the standard model, it means the world that you and I know and love, they get a mass through the Higgs mechanism, and the way to get it is here. And this tells you that the symmetry is broken. Remember I said, even if I give a gauge boson a mass, I can keep a gauge symmetry by adding extra degrees of freedom. But here, for example, the global symmetry is broken. I've actually broken not just some SU2 local, I have actually broken SU2. Here U1. I imagine the standard model where this will be SU2, but here U1 is broken because there is actually a massive particle which has nothing to do with the gauge freedom, okay, in this case. The symmetry is broken, charge does not annihilate the vacuum. Yes, please.
Since complete constants run, right?
Yes.
The mass will also run.
Yeah, mass is run.
And what happens with the vacuum expectation value? It also has like something.
Right, everything runs.
Okay.
It's an interesting thing. Everything runs in this world, and we'll have to talk about it. The moment we pretend we call them the constants, there are people who speculate they may change with time, even they may be okay. We hopefully not. That becomes a little messy, but it could be exciting, right? The laws of nature would change somewhat. The strength changes, okay. Obviously, if we change with time, they change very little. So we don't have to worry. On Monday, they're going to have the same value, right? We don't have to worry about that. Okay. Even if they change the energy, they change very little. But we can, change energies a lot. That we can do. We can change time a lot. Okay? I keep G because I want to work with this normalizable gauge. I want to do a computation, okay? So I'll keep G. Just in order to do a computation, then I'll show you how it basically disappeared. So there is actually a piece which is, there is a factor of Y, you agree? How will G couple? There will be a minus sign. H had plus, but this will have a minus sign, you agree, because there will be plus G minus G. So let me write it here to be explicit. FL bar, FR minus FR bar, FL. Am I right? Yes. I had plus IG, this is what? This is what? Please help me. This is IYG. And this will be what? Now one will cancel. 1 minus gamma 5 minus 1 plus gamma 5 will give me minus gamma 5. F bar gamma 5F. Do you agree with me? Well, obvious. All I'm writing is that 1 minus gamma 5 over 2 minus 1 plus gamma 5 over 2 is minus gamma 5. How are we doing? I think we can manage. We started a little late. You're not too hungry. If I take today 5 minutes, 10 minutes more, it may happen. We have to finish this calculation. I have to show you C independence. I'm going to erase this. Remember what we've learned here. All I learned that I had to choose the gauge the way I chose it. I had no choice. Everything was decided for me, but all I have to remember is here. This should not be erased. Make sure I don't erase this. Just tell me stop. So what do I have? From here, I have I. Let me not look at the, I will get the kinetic energy, and I'll get interaction with the gauge field, right? What will I get from here? There will be I times minus I. So there will be QL, FL bar, gamma mu, FL, plus QR, FR bar, gamma mu, FR, times A mu. Okay, today we have to be, this is what I got from here. Okay? Everybody following me? What is this? This gets 1 plus gamma 5, this gets 1 minus gamma 5. So I get QL plus QR over 2 F bar gamma mu F. Do you agree with me? I'm just picking a gamma mu piece. Once I will have QL over 2, and here I will have QR over 2. Okay? There is also the gamma mu gamma 5 piece. But this has 1 plus gamma 5, this has 1 minus gamma 5, so I will get QL minus QR over 2 F bar. I will show you this. This is, you will not find this in the books. 5 A mu, something interesting will emerge here. Notice that I have here the existence of Yukawa couplings forced me to have, was Emilio wanted to ask me, to force me to have a combination of charges in the following form. So notice here that, and I didn't want to fix QL and QR. I could have fixed just for fun. I can take QL1. Look, one solution is QL1, QR0. The other is QL a half, QR minus a half. They have to be different. Okay, let me show you that it doesn't matter. Okay, what we have here, so what we have the way A mu coupled, we'll have to keep it here. Look at the piece which is gamma 5. This is very interesting. This is fixed. QL minus QR is 1. So this is very important. Oh, I forgot G. There is a coupling constant G in front. From the covariant derivative, you agree? So I have A mu. Why don't I write like this? G psi bar gamma mu gamma 5 psi. So G over 2 plus QL QR. And it seems that I have a problem because I have something that depends on the charges. This is interaction with A. I shouldn't erase it.
Minus sign.
Why do you want a minus sign?
Because QL minus. No.
Well, I got it like this.
Okay, yes.
Well, actually, it came from the kinetic energy. So strictly speaking, this is minus interaction. Interaction in the Lagrangian we call with the minus sign. Okay. We'll talk about the sign when I do the. But this is just interaction I got from the Lagrangian. And here what I had. So let me summarize the. I shouldn't erase this. But I would like to erase this if you copied it. Can I? I'm going to erase this. Erase 1, erase 2, erase 3. Do it. Just do it, says Nike. Don't be scared. Okay. What about, let's clean this a little bit, Yukawa interaction. Here the minus sign. In the Lagrangian, interactions go with the minus sign. So what I've learned here, that why don't we keep it here? M fermion is Yukawa times V. These are fundamental relations that I need. So what I found, however, the interactions, so I find that Yukawa interaction has the Higgs interact as UY, but notice that Y is M fermion over MA times G. In other words, from here, Yukawa is M fermion over V, which is G M fermion over MA. Okay, trivial. G and G constant. So Yukawa looks like this, H psi bar psi. And this guy went with the minus sign. Minus IG psi bar gamma phi psi. If I call it a Lagrangian, actually there should be a minus sign because interaction goes with a minus sign. We will have double exchange, so the sign will not matter. Because typically what you write Lagrangian, you call a kinetic, which is generalized minus potential minus Yukawa interaction. So notice that the propagator of H, I can forget about H, but you've learned something very interesting, how the Higgs couples. Okay, this is our Higgs boson. Whenever we break the symmetry, there is an H field that looks exactly the same. In every case, it looks like this. And this is how it couples to we found out how it coupled to the gauge field. It's proportional to the mass. It couples again proportional to the fermion mass. This we will study a lot. Okay. So for example, if I ask you the Higgs field, who does it like to couple to of the standard model mostly? The top. Then what? Then tau and so on and so forth. You know, you can understand now why I'm going to have trouble probing the Higgs mechanism. It's not going to be easy because when I have light fermions, like up and down quark or the electron, this becomes terribly small number. And this is science fiction at the moment. I'll talk a lot about it. Higgs will be, this is why I'm studying symmetry breaking to such a degree. Higgs will be the main subject of this course, okay? This is where the action lies today.
For different fermions, Yukawa coupling changes?
Yeah, of course. Every time it's not universal, right? You have a coupling. It's just in the case of this is the way graviton couples. Graviton couples to you proportional to your mass. Every time it's different.
No, but we define mass through the coupling constant here. That's why I'm asking.
Well, or define the coupling constants for the mass. I don't know what comes first. It's a good question. But you didn't know this coupling. You were not going to remember this coupling. I would say the following. You remember the mass. So you say that I would think like this. The same thing I may have called about the gravity, how I normalize it, okay? I don't think, I say I know the mass, so I say the gravity couples to your mass. This is very similar to gravity at low energies. Gravity, of course, changes when you start moving fast. Gravity couples directly to light. Higgs cannot. There is a difference. But for slow-moving bodies, the guy looks like gravity, but he cannot compete with gravity. Why? It's heavy. It's a short-range force. It has nothing to do with gravity, right? Gravity is the important force when you go to long distances. The short distances is completely irrelevant, okay? Can this guy compete with gravity? Yes, and this is your homework. In the case of global symmetry, when it's a massless particle, okay? Massless particle propagate to large distances, okay? So then we have to work. Okay, in the Higgs case, G doesn't exist, so forget it. Okay, so now we are getting there. So I have this interaction, which is G psi bar gamma phi psi times I times G. No, why G? Why not I write it? G M fermion over MA I G psi bar gamma phi psi. This is all I need. I don't need the H field. I'm going to forget the H field because it does not depend on psi, its propagation. I have to now study the psi independence of physical processes. We have to look at some scattering amplitude, and we have to make sure, this is what is fundamental, that psi cancels. Physics cannot depend on psi. So that I can go in the unitary gauge where G doesn't exist. Okay. Then only I can be reassured. And I'm going to take a most natural process in the world. I'll take the scattering of two fermions. If I take the scattering of two fermions, the momentum P1 becomes P2, enters P3, or let's call this P2, I don't know, P3, P4. I can exchange A according to Feynman, and I can exchange G. I can also exchange H, but forget about that, that doesn't depend on C. Okay, there is nothing of gauge freedom in H. Okay, so I have to study these two different. This is our task. Without looking at the notes, becomes, if I make a small mistake, we'll be wrong. I claim that psi should independence. I believe in gauge invariance, okay? I'm at Hoft, I'm studying this, and I want to make sure that I show you this. So let me forget about the Higgs. I'll be talking a lot about the Higgs in the weeks to come. But today, let me forget that Higgs exists. These are two propagators that depend on C, and I have to see how magically they cancel against each other. And it's really magical. You know, this is how gauge invariance functions, okay? This is how gauge invariance, you will be learning QED. Magically leaves you with the universality of charge. Cancellations of Z2 and Z1. You're not doing yet loop diagrams, I presume, not yet, in QED. We're starting out. Self-energy, vertex correction. There is a magical cancellation between self-energy and which has to be, okay, I'll mention it in a month. So that we try to, have not just monologues, but I'll try it as often as I can to connect my course, to field theory course, to cosmology course, so that you keep seeing this interconnection. Yes, please.
What is A?
What is A?
I mean, is it a photon or?
Yeah, is it a photon?
I don't know.
Well, you know.
It's a photon.
No. It has a huge mass. I'm assuming that MA is not some negligibly small number, okay? Photon is so light that I can assume that it's massless. Let's define the photon. Photon is a massless gauge boson, whatever that means.
Yes, what confused me is this. Just take that one with me when you take MA to go to zero. I think we should recover the QED here, but what you recover is that also...
Well, it will never be QED, it will interact differently. Look at the way it interacts. This is not a photon ever. It's some different gauge boson. QED was a language of masslessness, okay? Remember I said it's not a good language. Maxwell was interested in massless gauge fields, okay? You know, propagation of a massless gauge field. He also couples it to charge and so on. But we use this language of Maxwell and Procca. By Maxwell we mean the massless gauge field. By Procca we mean the massive gauge field. Okay, when we talk of gauge field, that's a better language. This is not Maxwell. This is Procca. This is actually a Procca field. Only I'm working with this crazy thing, okay? You can work in unitary gauge. There is nothing wrong working in unitary gauge. There are no infinities. You will have a problem if you go to the limit of a small mass. You say, who cares? Why should I worry about that limit? Well, I say if you go to very high energies, okay, well, I'm never going to go to so high energies that this will explode on me, okay? So you can say, why are you bugging me here? Because the problem is genuine and it's reflected in non-realizability. So I have to take this fictitious particle. There are two fictitious things propagating here. There is a fictitious particle propagating here, and there is a fictitious thing here. Okay? The first piece, you notice that I don't have to worry about the first piece in the propagator. In other words, when I write this, well, well, let's start. So what's going to happen? Let's look at the A and B. And let's do A first. So how does A look like? There is a factor y from the Feynman rules, I times I. There is a factor y every time. It's just an oral sign. It doesn't make much difference, okay? Whether I include it or not, but I will, just for sake. So I have I g over 2 squared, you agree? Then I have two pieces, psi bar, gamma mu, gamma phi, psi. This is psi 2, no, psi 3 bar, psi 1. These charges are different. I don't have to write anymore, they're different. They're different, it's hidden here. If they were the same, I would never get gamma phi. So we can forget about that. We can forget about this. We don't need this. This we need. This is, then there is psi 4, gamma nu bar. Why do I write gamma 5? Gamma 5. No, why do I write like this? It's a mess. Gamma mu, gamma 5 plus QL plus QR psi 1 psi 4 bar gamma nu gamma 5 plus QL plus QR psi 2. Sorry, did I? Propagator, now I write the propagator. I have two. I could have stick in the propagator. The propagator has minus I. there is 1 over k squared minus ma squared. Then it has two pieces. One is the G mu nu piece. But let's not worry about G mu nu because it doesn't depend on C. Let me introduce that. Let me look at the C dependent piece. I want to calculate C dependent. Correct?
We're missing that C.
Now I should write this piece.
No.
I don't have to write this, you agree? This does not depend on C. That's why I didn't include H. Okay, we just look at the C dependent piece. So I have C minus 1 here times K nu over K squared minus C ma squared. This is the gauge boson exchange. The C dependent piece. Now notice, this is very important. You were saying that you are carrying a mass here. Look at what a mass you're carrying. Something that depends on QL, QR. And I didn't want to specify that. Now notice what K is. K is P1 minus P3. But it's also equal to P4 minus P2. Yes?
In principle, but we maybe QL, QR for the two particles may be different because there are two particles. Or
Yeah, of course, they're different. Not they may be, they are different.
So they must be different because we.
No, they are different.
Yes.
No, here it is, they're different. This is proportional to the difference of QL and QR. This was the equation. QL minus QR was 1 from the Yukawa interaction.
No, I mean we're scattering two different particles, so each one of them have its own QL, QR.
No.
You
I can
use-
still group it
you use-
together.
you could
I can
say-
still group it together, these two guys, if you wish. Well, okay, strictly speaking, okay, it's a question of language. I see what you're saying. Because they couple differently to the photon, you don't want to speak about the same particles. I can speak about that. Remember, the hypercharge, it treats differently left and right. And when you did the Z boson, you must have noticed that I speak of the electron, but and even you ask me, Nicolas asked me, should I speak of EL or ER about the electron? You can speak about the electron. Although EL, ER couple differently to the Z boson, that's okay. I call it an electron because there is one guy that the electron couples to universally. There are more than one guy. There is also a graviton, but okay, it doesn't exist in this course. But it couples to the photon. So I don't care, this is not the photon, this is some new gauge boson. This is the Z boson, if you wish. This is a prototype of the Z boson. Z boson will look like this. Z boson has different left and right charges. But I still like to speak of one particle. So now this is the important thing. This is a crucial thing here. K mu acting on psi, for example, P2, gamma mu, psi P1. Do you see what this is? Who is quick?
0.
It's 0. Because I have a K is P2 minus P1, okay? I'm using the well, I'm calling it C here, just this was F before, but okay, don't worry. F or C is the same thing. F is a fermion whose wave function I call C. P slash C is MC of P. So K has P2, then it acts here, and it has P1 and it acts here. So this is 0. So this doesn't contribute. It doesn't matter what the charges are. Okay, this is very useful. That we have a universal result which is independent completely of whether these charges are half, minus half, 0, minus 1. When it comes to the C-dependent piece, it's completely irrelevant. Okay. Now, that's the first thing. And this is just the Dirac equation. Let me see what you think will happen with this. K mu psi bar P2, let's see how quick you are, gamma 5 psi of P1. Is this 0? No, okay, let's see it, I'm glad. It's not 0, why? Because that's right what K mu is, that's, what did I say it was? P1 minus P2? Help me so that I have to go look. So when P2 acts here, it acts with a minus sign, gives me minus m. When P1 acts here, again it gives a minus sign. Why? Because we have to go through gamma 5. So this is actually minus 2m fermion. Psi bar gamma 5. Now the order doesn't matter. I can just write psi bar psi. There is no more K mu acting, there is no more momentum. What about
What is P3?
what about K mu psi of P4 gamma mu gamma 5 psi of P2? It's P4 minus P1, this will be 2mf. The sign has to be opposite because now K is flowing in, previously was flowing out. You see, now you can see why the cancellation may occur. The magic of cancellation is beautiful here. When I go on Shell, when I use a Dirac equation, I get rid of this ugly momenta and so on. I'm going to the psi bar gamma 5 side, but this is precisely how G interacts, okay? So it gives me hope. So now we better be careful with the signs and everything, because this could work. Okay, this is, Emilio.
Because the labeling is P3 in that one.
Sorry?
In the last, what we have been writing is P3.
It's better P3, you were saying.
No, in the first one. In the KD.
P3, P1.
Why not? It's even nicer if I do it correctly. And so this is P2.
Yeah.
Thank you.
The first one is also P3.
Sorry?
The first one is also P3.
When that is 0.
Yeah, the first one, the one that is 0, is P3 and P1.
Good, thank you. That's what I want you to be awake. I could read some notes, but I don't want to look, you know. This way I'm slow down, so I get, I have a minus sign here, and I have minus sign, so I got plus sign. And what did I get? But there is a minus sign times the plus sign. So I'm going to get minus sign at the end. And I will get G squared over 4. We'll cancel this 4. I'm getting there. MF squared. Then we have 1 over K squared minus MA squared. 1 over K squared minus CMA squared. There is C minus 1. And there is psi bar gamma 5 psi squared. This is the A contribution. The Xi-dependent piece. There was this G mu nu piece which we didn't care about because it didn't depend on Xi. It was manifestly Xi-independent, okay. It still sort of has to cancel non-trivial, okay? So we still have to be careful. Now here there is a factor of I, but I have to multiply by I to get the Feynman rule. So I get rid of this I, so I get G MF over MA minus sign is irrelevant here, squared, times the propagator, which is I over K squared minus C MA squared. So I have a common, this is good, I have a common, times psi bar. Notice I don't have to label the particles because it's just, there is no momentum flowing anymore, so I just call it psi bar gamma 5 bar. Strictly speaking, this is psi bar P3, psi bar, so on. Okay,
I think what Mahmoud was asking is if you have different fermions in both currents, then what will be brought in this expression?
I could look at some different process. Here I have only one fermion. I want to call this one fermion because I gave it one and the same mass. I'm using the Dirac definition of a fermion. I put the left and right-handed particles together. When I have two kinetic energies which have one common mass term, I call that one fermion by definition. How interacts with this? This is some imaginary gauge boson, okay? It's irrelevant. Think of the Z boson. In the case of the Z boson, the left and right charges are manifestly different. I don't know how much you've done the Z boson. See, this is why I was happy that Vishal did it, that thing, okay, because I would like you, I may have to say a little more about the Z boson, okay? The physics of the Z boson is fascinating, okay? And it's hidden in those decades. This has been the miracles of LEP is actually what they did for the Z boson to the precision, which is extraordinary, okay? In 1 in 1,000 or here we have now, you know, it's beaten.
I have a question. Look, here we used
Yes,
we used Dirac equations, or what we used.
yeah, Dirac equation is a good equation.
But when we take our new Lagrangian in overall and we drive the equation of motion,
we had a kinetic energy and we had a mass term. It's called the Dirac equation.
but we will have something with gamma 5, right?
But it has nothing to do with Dirac equation. That's an interaction with. Dirac has nothing to do with this interaction. Dirac equation is an equation for a fast-moving electron.
Yes.
I'm confused. This is just an interaction.
I see.
Dirac equation is, I'm just saying, these particles are real fermions that propagate. These are external particles. They propagate it according to the laws of Einstein, which are hidden in the Dirac equation. E squared is equal P squared plus M squared. This is what I mean by the mass term, if you wish. Okay? A particle, this fermion satisfies this. From here I derived that E squared is P squared minus M squared. This is why I can use, I'm sorry. It's not, I'm not taking it lightly. I just want to, you know, I'm enjoying it to make sure that we understand that this is a good old electron here. This is electron scattering on a Z boson with exactly like this. With some minor coefficient change. We can repeat this and do the Z boson, you know, C independence. That could be a nice take home on the exam. We could, or a homework problem in which you look at all the particles and see these intricacies. But look here. Let's first things first, so let them up. So from here, A plus B. Now I'm a little nervous because if it doesn't cancel, I have I G square M fermion square over MA square is common? No, it's not common. Why am I rushing?
You can make it common.
I can make it common, he says. Okay. Let's make it common then. Let me make you happy. Actually, it's better to make it common. So what do I get? I can take psi bar gamma phi psi squared. This is common, right? Let's take what is common. Is there anything else common? Yes. 1 over k squared minus CMA squared. That's common. So what do we have? From the second piece, let's say. It's just 1. Am I right?
Minus 1. No, 1.
No, plus 1. Okay, 1 minus, because there was a minus sign, C minus 1 MA squared, because I took it as a common factor, K squared minus MA squared. I think now I should be okay. This is, let's just write what this is. This is K squared minus MA squared plus MA squared minus CMA squared divided by K squared minus MA squared. Agree? MA squared cancel. And I'm left with k square minus CMA square. Here cancels. Let me do like this. Lo and behold. Yes, we can. Okay. It's not a big deal. The thing is to do this to all other perturbations here. You can see apparently there can be studies. There can be studies that did the following. They studied people who exercise a lot. And they found out that it's very important that for your health to exercise a lot. But apparently it's also as important to believe that you exercise a lot. In other words, they would have two categories of people. People that exercise a lot but felt that they didn't do enough, they would do exactly the same amount of exercise. And those that felt that they were doing a lot. And apparently it's very good for you to feel you're going to be healthier. So it may help you in your work. I'm sorry. It's not a very smart. You feel good when you do. You can say this was trivial, right? Oh, did I? Yeah, it cancelled. So what did we get? What was the overall sign? It was +1, right? So we were left with I, G square, MF square over MA square. Then what remained? 1 over K square minus MA square psi bar gamma phi psi bar square. This is what I got. A plus B. Two things very interesting here. No, a number of things. You see, I can just say it cancelled, okay, and this is a point when I want to emphasize, okay, when you do something, keep staring at it and keep analyzing it. We really appreciate in your homeworks when you give a result that you go over it, that you check the dimensional things, that you get the physical arguments, that you check the symmetries, that you look at the certain limits, okay. It will be good for you, it will impress your grader, your tutor, and your professor even more. So here, what I can now look at, where you think. First, I've proven, and I'm happy. I'm simple-minded. I don't need a proof to all others in perturbation theory. I have never gone through this proof. I'm not, if you think a formal field theorist, okay. I've been happy to see it in some of the calculations I've done. I've done it also at the loop level. I will consider it proven. And this little exercise will be a proof that what Et Hoff did is actually solution to the problem of renormalizability. I can work in this gauge, the propagators are perfectly well behaved, at the end of the day Xi cancels, and you can think of that as a unitary Proca limit. In that limit, when Xi goes to infinity, there is no this guy, and you are in the Proca case. But let's now study this a little more. Let's look at various limits, right? No, why did I? Oh, where is my result? Aha, I should. Let me erase this. And let me keep the result. So I got, there was factor of I, G square, MF square over MA square, 1 over K square minus MA square psi bar gamma phi psi square. Remember, I didn't incorporate this piece here, but this was psi independent. Notice a very important limit I can take. Let's see what happens when G goes to 0. When G goes to 0, what should happen physically? A decouples. And it is manifest here. Any contribution from A will disappear because G goes to 0. It decouples. Doesn't depend what these charges are, it's irrelevant, okay. When there is no gauge coupling, of course, that phantom field practically doesn't exist. There will be millions of fields. If they don't interact with us, we don't give a damn. What happens here when G goes to 0? Well, it feels like this is going to 0. Does it?
No, because we have the
MA goes to 0. Why it's important that it doesn't go to 0? When G goes to 0 means that I'm back into a global case of a Nambu-Goldstone picture. So Vg goes to 0, I should recapture the Goldstone boson. I claim to you that there is a theorem, and you have seen it, that when G goes to 0 in a Goldstone case, I have a massless particle, and it's nice when G goes to 0. This goes into I, m fermion square over V squared, ma is GV, 1 over K squared, psi bar, gamma phi. This is called a Nambu-Goldstone boson. The characteristics of Nambu-Goldstone boson, remember it's a phase, the Nambu-Goldstone field. It's the imaginary, when I expand it, it's the imaginary component, it couples with extra I, or being a phase, it's always going to couple to the axial, to psi bar gamma phi psi. And Goldstone bosons are proportional to the masses. I'm gonna profit and say a few words more. Just have to say a few words more, and I will be happy to see if there are questions. To really grasp the Goldstone picture. The Higgs picture I'm happy with. I have nothing to say more about the U1 Higgs case. I mean,
The little will change in case we make the scattering between two different fermions will be that the mf squared will split in mf.
yeah, there will be two different masses precisely. I can take two different fermions. I can scatter. Thank you. I can scatter later on electron. And why don't we do that later on? We'll scatter an electron on the downpour and check the Xi independence. And your guess is precisely. And in the end, you're going to show Xi independence, and this will not be m fermion square. It will be m electron times m downpour. The coupling of Goldstone fields is universal. It was always, you see, it was the gamma phi piece there. It was the imaginary component. It was coming from the phase. So the leading coupling had gamma phi. It was proportional to the fermion mass. You change the fermion, you will change the mass. So, and it's hidden here, and this is very profound. Now, remember what I said. I said, when I spoke of Goldstone, I said, well, I can also get rid of that field and put it in the kinetic energy. Remember I said, I depend how I work with, if I work with a phase. And then you get the derivative coupling. Remember I said I actually can show that the coupling of the gauge bosons can be hidden in the derivative coupling. And here some psi bar, gamma mu, whatever pieces, I don't care. It seems that there is a contradiction, because now you can tell me, but look, when momentum goes to 0, this guy decouples. But look at your guy is coupled when momentum goes to 0. This is a whole problem, okay? I can just remind you how it works. When momentums go to 0, you should go to non-relativistic limit. In the non-relativistic limit, remember how psi looks like in the non-relativistic limit, which is very important. You want to understand the physical coupling of a slow-moving guy that you emitted with little energy, not slow-moving. This guy is massless. He never moves slowly. Okay, I'm sorry. How does psi look in the non-relativistic limit? It has only one component, right? Two component spinner. There is no reason then to speak of, we can just go into the usual picture of spinners. And then we get, there is a large and small component. Because in non-relativistic limit, just to remind you, you don't have to reproduce it, I said in the homework, we take gamma 0, which is diagonal, and gamma phi, which is off diagonal. Notice here that there is a product of gamma 0, gamma phi, so it doesn't depend, the interaction doesn't depend on the conventions, okay? It's just that with this gamma 0, it's easier to see what is going on. If you choose the other gamma 0, then thing would look more complicated and the results would be the same. Okay, so notice that there is, because this is off diagonal, you see this is psi dagger, gamma 0, gamma 5, psi. This is off diagonal. It will pick up a momentum that you will see in your homework. The Goldstone boson is very neat, okay? In relativistic couple, they couple less and less. I can look. So, I mean, forget what I said. This is just, if I go another picture, this is correct here, okay? It is, it is proportional to fermion mass at first glance, but when you go to small momenta, notice that you will get 1 over fermion mass. The fermion mass is going to disappear. Something else will happen. This thing, sigma, what is sigma sandwich between you? That's called, someone said I heard, no? That's called? Spin, thank you. It couples to the spin. Cosmology are very peculiar. Graviton couples to your mass. Higgs couples to your mass. But the Goldstone boson doesn't couple to your mass as it looks here. Okay, well, when it's relativistic, maybe it does. I don't care when the particle is relativistic, okay? But in the physical limit that you and I can probe, you know, we understand the world when we don't understand. I hope you have the same problem as I do. I can still don't understand the photon. I was like 4 or 5 years old when my brother tried to teach me relative velocity, and I couldn't comprehend. And then our father took us for a drive. And someone was trying to overtake us. My father didn't like us to be overtaken, so we were going parallel with this. We were going fast, you know. It was both exciting and educational, because my brother told me, look, how fast we are going. Very fast. I can see that the trees, you know, well. But you see that the velocity between us and this guy is 0. And I was so happy. I understood relative velocity. I'll never forget that, okay. I loved understanding and I love my brother. But before going to bed, my brother told me, okay, but you know there is a thing which we call light. And it always goes with the same speed. Doesn't matter how fast you go. Of course, my first reaction was going to be that I don't believe in that, right? But I knew that my brother was smart, so I had to believe that, okay? To this day, I feel the pain. I hated my brother that night. And I still hate light for this, okay? I don't understand how it's possible, right? How in the world is that possible? It's true, apparently. I don't doubt it. So the real understanding comes when we go to non-relativistic limit. Whatever you do, you try to see in the non-relativistic limit to see what is happening, you know, non-relativistic potentials. And here, the stories will be the homework. I want you to think why and how this would compete with gravity. We have to understand why Goldstone bosons can exist. Because gravity has been checked at all kinds of distances. Okay, so Cavendish experiments, and we know a lot about gravity. And we have to make sure that if you have a massless particle, it doesn't spoil. Gravity, this will propagate to all distances. Okay. On this note, we can finish today. So I'm actually on time. We started late.
In this whole calculation and discussion, we looked at the excite-dependent part.
Right.
So that was actually also the coupling with Higgs.
Yes. There will also be the coupling of Higgs. There is also a coupling to the, I can go to the limit G going to 0. Okay, thank you. There will be, in that case, there will not be gauge boson, but there will be the Higgs. But the Higgs is heavy, so the force is very short range. It doesn't affect anything that we know about the microscopic world. This I want us to, we have to understand, really. Just because there could be Goldstone bosons, we have to understand them deeply. They propagate to all distances, and yet they do no damage to the world that we know. After the homework, I'll discuss, we'll just say, 10 more minutes about possible Goldstone, something else very nice. But after the homework. So, here is our result that we can study. Hopefully, you said there will be also here exchange, which will be G squared m fermion squared over ma squared. Okay, just what Mechman told us, there will be 1 of k squared minus ma squared. That's a separate contribution, right? It would go like this. This was the coupling of the Higgs, remember? It was proportional to m fermion over ma. And then it would look psi bar psi squared. This is how Higgs contributes. I'm glad you asked. It should be, you see, when ma is large, they of course are comparable. and must be taken account. Higgs is not much heavier than the gauge boson. So if you keep this contribution, you should keep that contribution too. You agree? You cannot neglect it. But you see how nicely we got the fermion mass. It came. You can now forget, because all I did to cancel the C. We could have gone nicely to the maybe next time we spend a few words. But no, it doesn't make sense. We could have gone immediately to the unitary gauge. What would happen in the unitary gauge? There would have not been D. There would have been this guy. 1 over ma square would be manifest there. That's what I got. There will be g square over ma square. I will get the fermion mass when I go on the Dirac equation. I will see immediately I have k mu, there will be no psi. I will have k mu twice, and that will bring the fermion mass twice. So you can see it in the unitary gauge is much better. Whenever you can see things in the unitary gauge, whenever you wanted to show the cancellation, please check it, because sometimes even loops, there may be cancellations. It's great to do that and see explicitly how the normalizability works in the Broca case, when it's possible. And we live in the world in which MH is not so different from MA. Right? MA is around 80, 90 GeV, depending whether you speak of W and Z, and the Higgs mass is 125. It's a very similar number. Any last question, public?
When set G to 0, then we are left with some limiting result of that expression, which shows how the diagram with particle G, propagator of G, contributes actually. Right?
When G goes to 0, then of course this will dominate. Imagine at small momenta this will dominate a lot, because Higgs is heavy. At small momenta this will be irrelevant. Of course, at very large energies you have to include both. But maybe that was not your question.
What I was confused about, when we try to gauge the massive boson using the new field G, we talk about the fictitious G particle or field that we cannot observe, or can we observe the G?
This guy?
Yes, when we...
No, sorry. G now, wait. Let's be careful. G is the coupling and G is the field. Don't say G, say
Goldstone.
Nambu Goldstone. Well, in the Higgs case, that guy doesn't exist. I got this not because of that guy. I got it because there is K mu, K nu.
Yes.
I don't have to speak of this guy if I know how to compute. I can just speak of Broca. I got the psi bar gamma 5 piece because K mu gave me there through the Dirac equation. So there is no Nambu Goldstone field.
So for small g equals 0, we don't have gauge invariance because we are not gauging anything at all.
For when the coupling goes to 0.
Yes, small g.
Yes, when the coupling goes to 0. Thank you. Then we are left with the Goldstone boson,
which is not fictitious.
That particle then exists. I cannot gauge it away. How did I eliminate that Nambu Goldstone field, the capital G that we call it? How did I eliminate it? By doing a rotation using the gauge freedom. That disappears. If I try to do that, it will reappear. You know, you can always perform that rotation if you wish, but it's not the symmetry. You will get it in the kinetic energy. You see, this has to be understood to the bitter end. You said, oh, I can. You could have said, I wrote then I said, let me, phi goes into I to the minus G over V plus H. You can say, oh, I will do that even in the global case. Well, I can do that. I can do anything I want. I can try to rotate this guy away. It will reappear it will disappear from the potential, but will end up in the kinetic energy. when you do that, remember, psi must transform also, because psi carries this u and psi. You may perform this rotation, but it's not the symmetry anymore. Then psi L goes into e to the minus I don't know, some number, g over v, psi L, and psi r goes into e to the, it will have the opposite charge. So you will get this in the kinetic energy. It's worth doing it. I wonder whether that exercise, you see, from the psi L gamma mu d mu psi L plus left going to right, since their charges are different. If I perform here this rotation, I must perform it on the fermions. I always do everything simultaneously. Notice I had a covariant derivative. That, of course, it will be invariant under such a, but not an ordinary derivative. So I will get here interaction, this d mu g over v, and you will get psi bar gamma mu gamma phi phi, something like this. Maybe there'll be a gamma mu piece. Okay, let's do, what will happen, because left is right is different, what will happen is the following. There will be, with some coefficient I, psi bar gamma mu psi, plus some coefficient B, psi bar gamma mu gamma phi psi. Do you see this? How it will emerge? Because the air transformation property will have different things. What will happen then? Just bear with me. You can do now partial integration. This will become g over v. Then you take the derivative here. But d mu acting on this current we saw was 0. This is the Dirac equation, conservation of vector current. So you will get d mu of this. But this will be g over v, a times 0, because this current is conserved. And this will give me m fermion psi bar gamma phi psi. You get the same interaction. That's a beauty of the. And there is 1 over v, but 1 over v is g 1 over ma. You will get the same interaction. You can do that. The Goldson-Mosley mistake, no matter what you do. Okay, please try to understand it in all possible ways. Okay, that there is never a confusion. And this could be. It could be maybe, okay, I have to think of whether there should be an exercise or I can do it. It could be a nice exercise that you say, aha, let's do this unitary thing we did in the case of a global symmetry, and then let's reproduce the coupling of the physical coupling should be the same in the end when we go on chat. That's it. We are all getting hungry. I'm more than you. They have time to. Anyway, let me